we introduced the problem, we said that the molar flow rate is given, and what we wanted to do, and the inlet conversion was given. And what we wanted to do was, in that problem, maximize the outlet conversion. So we looked to see which arrangement of the reactors gave us the largest outlet conversion. That was the question. I expect both you and Sean to be here every class. You weren't here last class, and neither was Sean. You're supposed to be in class to be able to answer questions if you have a student. If you don't come to class, you can't answer the questions, and you will not get credit for the TA if you're not here. Make sure Sean knows that. And if you're absent again, I'm going to drop you. Same thing with him. You have a responsibility to the other students in the class. And part of that responsibility is to be here. And I'm making sure to say this so everyone can hear it. Because it's irresponsible not to be in class for the TA. Are there any other questions? Okay, if you remember last time, we were looking at a situation where we were trying to build two reactors, two CSVs in series. And we look at -1 over RA versus X in out. We have a curve. Down, go up, we went up, went the other way. And had we built a single CSTR, and we had tau for a CSTR, was CA0 X out minus X in over minus RA out. That's for one CSTR over and of course we know that tau plug is CA0, the integral X in, X out, dxa over minus RA. The difference being here, minus RA is a function of XA, and here minus RA is just evaluated XA out. So for a plug flow reactor, tau over CA0 is just the area under the curve. However, for a single CSTR, tau over CA0 is just the area of this rectangle. One CSTR. So we saw that we can do much better. Sean, I will repeat this. You were not here in the last class. If you miss another class, I will drop you and you won't get the TA another class. You're expected to be here every class. You have a responsibility to the other people, to all the students in this class, to be the TA. If you don't show up to class and know what's going on, you can't be a TA. Is that clear? Okay. So this would clearly what we'd like to do, if XA out is given, we would like to minimize tau over CA0. Because tau, we know, is CA0, V0, V over FA0. And clearly minimizing tau means either making a smaller reactor or having a larger molar flow rate, so we get more product. Clearly that's a good thing, assuming the product is desired. Okay, so we saw that clearly there's, when the rate function looks like this, that is, the rate is monotonically decreasing with concentration, as monotonically increasing as concentration increases, and the curve looks like this, clearly the plug gives a smaller area than the CSTR, but there are many situations where one, for other reasons, has to use a CSTR rather than a plug flow reactor. What examples did we give in the past for that?
If you have like an exothermic reaction that's happening, that these
Because
it can blow up.
CSTRs can blow up also, but it may be used to do cooling. So if there are certain heat effects that are easier to manage with a CSTR, with mixing, then we might be forced to use a CSTR. Well, so we saw that if we're forced to use a CSTR, but we don't want to pay this penalty of this extra area, we might go for 2 CSTRs in series, in which case we save this amount of area at the cost of building 2 reactors. So the sum of these two is tau 1 plus tau 2, 2 CSTRs in series, and this region is the savings. And we saw in a generic sense that we do the best. That is, in a generic sense, we saw that the savings looks like it would be best if we move this point around. This point is x1. If we move this around until we get to a point where the diagonal is parallel to the tangent to the curve. We did that in a generic sense. And then we looked at what happens when we have an nth order reaction. We have an nth order reaction. Nth order reaction is clearly monatomic because the rate goes, what is the rate function for an nth order reaction? What is minus RA? KCA to the n. Good. So clearly, as long as n is positive, this is monatomic. So we went through and we noted that n is equal to 1, n is less than 1, and is greater than 1. When n is less than 1, then we usually want the big reactor first. When n is equal to 1, we want V1 is equal to V2. And when n is greater than 1, we want V1 less than V2. And we said that basically we want to take advantage of the faster rate. Typically we want to take advantage. And so at least for the n is equal to greater than 1, it seems to be intuitively clear. If V1 is small, then V1, the first reactor, is operating at a higher concentration than it would be if V1 is larger. So as a result, the rate is faster. So therefore, I could get away with a somewhat smaller reactor. Now, of course, you don't want to carry that to extremes. If x1, if the first reactor is really, really tiny, then this line moves all the way over here, and you pay the penalty. It's so small, yes, it's reacting quickly, but you're not reacting very much stuff. So there's a balance there, and that's why that pushes it over here. On the other hand, if you move this too far to the right, you're reacting a lot of stuff, but you're reacting it slowly. And that balance comes out that V1 should be smaller than V2 when n is greater than 1, greater than V2 when n is less than 1, and equal when n equals to 1. And we looked at the situation when n is equal to 1, and we calculated that x1, the best x1, is equal to 1 minus the square root of 1 minus x out. Is that right? What did we call it? We called it x2? Please shut off your cell phones. It's annoying. Make sure it's turned off. If you're expecting a call from a hospital, then put it on vibrate. Okay, so let's just demonstrate that in fact this gives me the right, that V1 is equal to V2. So again, notice that tau over C is V over F. So let's look at, for the first reactor, tau for the first CSTR divided by the volume of that reactor. I'm sorry, divided by CA0. That's the volume of the first reactor over FA0. And what's that equal to? Well, that's, we know that's equal to, from the formula, that's equal to, and what we have here, the situation we have here, is 2 CSTRs in series. So I've got 2 CSTRs in series. 1, 2. So we call this x1, x2. And I'm going to choose the inlet I'm going to choose my reference state at inlet to first reactor. For this particular example, I'm going to choose that. I don't always have to do that. Choose reference state at inlet to first reactor. So in that case, this is going to be x0, x in is 0 because of that choice. X in equals 0 because of that choice. Okay, so now let's plug into this equation. X out of the first reactor is x1, which we said is 1 minus the square root of 1 minus x2. Divided by minus RA there. So minus RA is K times CA0 times, actually let's just see if I, yeah, K CA0 times 1 minus XA. So let's write this 1. I'm skipping a step here. So why don't we write this out? This is x1 minus x0, 1 minus x1. And if I've done this to the optimum, I'm going to have an x star there. By choice of reference state, this is 0. It'd be nice if people showed up on time. Okay, so x1 star is 1 minus the square root of 1 minus x2. x0 is 0. And here I have k CA0. And 1 minus x1 star, 1 minus 1 is 0. Yes?
Shouldn't this be a nth order reaction? Oh, sorry. Didn't see that.
Okay, and 1 minus x1 star is 1 minus 1 minus this, just gives me the square root of 1 minus x2. Remember, what we're doing now is we calculated, for n is equal to 1, we're going to show that v1 is equal to v2. In order to do that, we first maximized this area, get x1 star as this, and now we're calculating what the volumes are. Here's an expression for v1 from the design equation, and we'll relate this to an expression for v2, so you know where we're going. Okay, so let's multiply top and bottom by the square root to rationalize the denominator. So I've got k CA0, 1 minus x2. And in the numerator, I have a square root of 1 minus x2 minus 1 plus x2. I just multiply top and bottom by the square root. Okay, so let's notice now that this thing in the bottom, k is 0, k CA0, 1 minus x2 is what? What is this equal? Yes, very good. It's the rate expression for the second reactor, because CA0, 1 minus x2 is CA2. So this is minus R2. Let me use the right same notation. Use any notation there. Minus RA for reactor 2. And in the numerator, I have this thing. Well, this is x2 minus a minus 1 minus this. Well, let me rewrite it. It's x. I can write this as x2 minus 1 minus the square root of 1 minus x2. But this thing in here is just x1 star. So I have x2 minus x1 star over minus RA2. X out minus x in over minus RA out. That's just equal to tau over CA0 for reactor 2. Which is just V2 over CA0. So what we've shown from this chain of equalities is V1 over FA0, this is an FA0, is equal to V2 over FA0, or V1 is equal to V2. So for n is equal to 1, we just showed that V1 is equal to V2. Are there any questions on that? Okay, so what I'm going to do now is, well, let's see what we're going to do. Let's just review what we've done so far in the last class. We started out when we were looking at steady-state flow reactors. We looked at two types of reactors. What were the two types of reactors we looked at? Plug flow and the CSTR. And we came up with a very nice, of course very nice because I made it, little sheet with all the design equations. And then what we say is, well, these are extremes. Plug flow and CSTR are extremes of what concept? What concept is the plug and the CSTR extreme examples of? Opposite extremes. It's a one-word answer. I don't need a whole story. This isn't the presidential debate. What are they extremes of? John? CSTR and plug are extreme examples of one concept. What concept is that I've used 100 times? Mixing. The CSTR is infinite mixing, if you like. And the plug flow reactor is zero mixing. And in principle, I have a continuum here, but the plug is zero and the CSTR is infinity. And what we saw is there are some reasons having nothing to do with conversion why we may want to choose a plug or a CSTR. We may be stuck with them. But as far as conversion goes, sometimes I want, for monotonic reaction rates, monotonically increasing reaction rates, I should always want a plug flow performance. For monotonically decreasing reaction rates, I should always want a CSTR performance. And for more complicated reaction rates, I might want something else. But sometimes the extraneous or other issues, such as, for example, heating effects or sensitivity of a reaction of a certain catalyst mixing, may dictate that I have to use a different type of reactor than I would like for, if I were only worried about conversion. So as a result, we started looking at what happens when we look at different combinations of plugs or CSTRs. So we looked at reactors in series and reactors in parallel. And for the plug flow systems, we saw there wasn't anything particularly exciting by taking plug flow reactors in series or in parallel. That's one of the few things in this course that are not exciting. What we saw is that when we take plug flow reactors in series or in parallel, they're basically equivalent to one big plug flow reactor. So why build more than one reactor? It's usually cheaper to build one reactor than to build 5 reactors. On the other hand, for CSTRs, the story was a lot more interesting. We saw that when we arranged CSTRs in series or in parallel, there was a big difference, and that we were usually better off arranging them in series. And then there was some sub-details about if the reactors were different sizes, what order should we put them in. But the gist of arranging CSTRs in series was to benefit, to get from the pure single CSTR performance to something that's closer to a plug flow performance. And we saw in the limit, as the number of CSTRs goes to infinity, and the size of each CSTR goes to 0, that we can get exactly plug flow performance. We never want to build 1,000,000 CSTRs, but conceptually it's good to know that we can get the more CSTRs we build, the closer we can get to plug flow performance. Usually 2 is good enough. Because 2, there's a big saving. The incremental savings in going from n to n plus 1 is the highest in going from 1 to 2. Okay, so that tells us that if there's something about plug flow performance we like, but we're forced to use a CSTR, we can move along this continuum from CSTR to plug by using CSTRs in series. However, what we saw in using series and parallel arrangements of plug flow reactors was that that doesn't work going the other way. So what if we're in a situation where we have a plug flow reactor, where we stuck using a plug flow reactor. We have a very sensitive catalyst. We can't mix it. You mix it, you destroy it. Yet, the reaction kinetics are such that we really want CSTR performance. What do we do? Well, yes?
I was gonna ask, can we put both CSTR and plug flow users?
Sure, sure. But I'm looking, we can do that, and of course, every arrangement you can analyze. But the question I just mentioned was we have a situation where we can't use a CSTR because it'll destroy our catalyst. So using a CSTR and plug will still destroy the catalyst.
Well, what I mean, for example, we could say, mix our reactions and then make them go through a plug flow reactor, and then pass to say another CSTR to our.
Yeah, but again, the catalyst, yeah, I'm giving you an extreme example where the catalyst can't take mixing. It would destroy the catalyst. It's sort of like the medical issue where the operation was a success, but then we killed the patient. Okay, so we don't want to kill the catalyst. We made a really small reactor, really efficient, but there's no reaction going on. Okay, so we're going to look at what possibly we could do there. And I'm going to need a lot of blackboard space. All right, so I'll use all these blackboards. So let's see if we can think what to do here. Again, CSTR is the idea of infinite mixing. What does mixing mean? What do you have to do to mix? What does mixing mean?
There would be a difference.
Yes, very good. So mixing means if you take two streams that are the same composition, you mix them, that doesn't count as mixing. Mixing is when you mix different things, not things that are the same. So CSTR is infinite mixing. The plug flow reactor has zero mixing. If I want to make the plug flow or something, we're starting with a plug flow reactor and try to get it to a little closer to CSTR performance, what do I need to introduce into the plug flow reactor? No, you just answered after you. Are you listening to anything I'm saying? Anything? Is anybody awake here?
Can we add catalyst, make the flow turbulent?
That'd baffle.
The CSTR is infinite mixing.
Oh,
The plug flow reactor is zero mixing. If we want to get this plug flow reactor looking a little more than like a CSTR, what do we need to introduce to the plug flow reactor?
A baffle.
A mixer.
A baffle. Right?
What concept do we need, not what piece of equipment, what
Oh.
concept do we need to introduce to the plug flow reactor in order to make it look a little bit more like a CSTR?
Mm.
Different flow rate.
Different stream, each stream.
You can't stir.
Change the inf order.
Okay, I don't know how I can lead you to it anymore. If you have infinite mixing and zero mixing, and you want to make this look a little bit more like this, you have to introduce some type of mixing. Is that so complicated? I guess it is. Okay, so we need some, and mixing means combining streams that are different. What streams are available in a plug flow reactor? Hello? If I ask him a question last, don't look down at your book, because you're the next one who's going to get a question. What streams do I have available in a plug flow reactor? Okay. And those streams have different compositions. If I want to introduce mixing, how can I possibly introduce mixing with those two streams? Volunteer? I can try recycling. So the idea here is to try to take a little bit of the outlet and put it into the inlet. That's the only way I can do any mixing in this system. And this is called the recycle reactor. simplest form of recycle reactor we can think of. So let's, yes?
You're not talking about diffusion.
Did I say the word diffusion this class?
Because how would that mix? I mean, how would that introduce mixing?
I'm sorry?
I don't understand how that introduces mixing.
If you have any reaction going on, the outlet stream is different from the inlet stream. If I combine the outlet, part of the outlet stream with the inlet stream, I'm combining streams that have different composition, and I feed them into the reactor together. Now, if you're asking, how am I going to get them to talk to each other, I assume that they're going to diffuse amongst each other, or I can do very, very soft. Typically, I can arrange for them to be mixed before they enter the reactor in a very gentle way. I don't need a stirring rod to do that. Either I can have it go through some sort of geometry where it mixes, or diffusion is probably going to be too slow. But I could just go through some geometry, say a zigzag pipe. Usually I don't even have to do that, I just mix them. Because the flow here is perpendicular, so by the time it turns and combines, they're mixed. Okay, so what we'd like to do is we would like to analyze the system. So I'm going to define different points along the way. I have the inlet. I have the outlet. Now after this combines, I'm going to call this point 1. Point 1 is what actually is going into the reactor. Point 2 is what's actually coming out of the reactor. I want to get the numbers consistent. Yeah, 3 is the recycle stream, and out for out, I'm going to use F for final, so I don't have to write the word out all the time. And the only other thing I need, so I've got in 1, 2, F at 3, and then of course I need my reference state, which is somewhere out, could be before it enters some other piece of equipment. It might be the inlet here, it might not be. And what we're going to do is we're going to come up with we're going to complete a little table, a little chart. And the chart is going to contain all these positions. In, 1, actually I probably want to do these in rows. In, 1, 2, 3, F. And what would I like to have in this chart? Well, I would like, in order to come, let's work backwards. In order to come up with the design equation for this reactor, I have the design equation is I have a plug flow reactor. So for the plug flow reactor, I've got tau plug over CA0. CA0 is at the reference state. Is equal to, what is the design equation for the CSTR? I'm sorry, for a plug flow reactor? Did I wake you up? What? Tell me on this chart. That's the important thing. What's in and what's out on this chart? With this notation, it's an integral. Please speak up. I can't hear. In, it's the integral from here to no.
Integral from n to 1.
I can't hear
The
you.
integral from n to 1.
The integral from in to 1. Do you see a plug flow reactor here?
From 1 to 2.
Is this a random guess? How many how many combinations are there? I've got 2, 4, 5. So I've got 5 choices for the first and 4 for the second. So you give me all 20 possibilities until we get to the right one. Which one is it?
From 1 to 2.
Right? From why is it from x1 to x2?
You're integrating over your plug flow reactor.
Because that's what's going into the plug flow reactor and that's what's coming out of the plug flow reactor, not in and out of the system. The design equation is for the plug flow reactor. And what's inside here? In the integral? dx. I can't hear you. divided by minus the rate, minus RA. Okay, so in order to do this, I need to know x1 and x2. That's clearly something I would like to know. So I need to know x1. Actually, let's fill it in. I'm going to need to know, move this up a little bit. X1 and X2. I'm sorry, X1. I'm going to need to know X. I'm going to need to know the X's of everything. Clearly, I'm going to need to know the X's. In order to know the X's, I get the X's from the concentrations. So I'm going to need to know the concentrations. To get the concentrations, if you remember, CAV is equal to FA. So CA is related to FA and V. So I'm going to need to know V and FA to get CA. And we'll see if I need anything else. That may be all. Just don't bother having it in my notes. And I'm going to want to do this in general for a situation where I might have linear volume expansion. So I have some sort of, I'm allowing for an epsilon A not equal to 0. And let's remember some of the reference equations. What is CA? Let's start with VA. How does V? How does V relate to XA and the state? state? Had this in class, right? How does V relate to the reference state? To XA to the V0 at the reference state. Take your notes. And how does FA relate to XA? You should know this. I'm sorry?
1 minus
Yeah. Okay, and we also know that CA is equal to FA over V. So that's equal to FA0 over V0, 1 plus epsilon A XA, I'm sorry, 1 minus XA over 1 plus epsilon A XA. And this thing is just CA0, the reference thing. So the first thing we can do is we can fill in everything at the inlet. The inlet is V0, 1 plus epsilon A X in. FA is FA0, 1 minus X in. X at the inlet is X in. And CA is CA0, 1 minus XA in, over 1 plus epsilon A XA in. Now really all we want is X1 and X2. It's the only things we need here. So to get X1 and X2, X2 we can get right away. Because presumably we know the inlet and the outlet. So I'm allowed to leave things in terms of X in and X out. So, and what I need to define here is something called R, which is called the recycle ratio. And I'm going to define R as V3 over VF. So it's the ratio of what goes recycled to what comes out. So what you can see, the way I defined it is if there's nothing in the recycle, then the recycle ratio is 0 because V3 is 0. If everything gets recycled, total recycle, then R is infinity because VF is 0. So it goes from 0 to infinity. Okay, so what we would like to have, as we said, we want x1 and x2. So let's only fill in the parts of the chart that we need to get to x1 and x2. So if I know x out, what's the relationship between x out and x2?
Me? They're the same.
They're the same. There's no reaction going on here. How about between x out and x3?
They're the same.
They're the same. All three of these are the same. It's the same stream that's just getting split up. So x2, x3, and x out are all the same. That's easy. How about x1? Well, x1, stream 1 is a mixture of the in stream and the 3 stream. So I don't know what x1 is. In order to get x1, I probably have to get x1 once I know CA1. So I have to fill in this box in order to get to this box. To get CA1, I need FA1 and V1. So I got to fill in these boxes. Except one column too many. Well, okay, but how do I get FA1 and V1? FA1 and V1 are a mixture of the inlet stream and the 3 stream. So I need to know the concentration in the 3 stream in order to know how to mix it with the 1 stream. So I need to know everything about the in stream and everything about the 3 stream. So I'm going to fill in these boxes to figure out the 3 stream. And once I've gotten the 3 stream, I know how to get the out stream. I might as well get those. That's easy. But what I absolutely need is I need all the boxes in this row and to get all the boxes in this row. It turns out the other boxes are trivial, 2 and F, so I'll just fill them in for completeness. So let's go through and let's fill out the out stream. The out stream if I consider this dashed box, a black box, then the outstream is, I've got the reference state that's coming somewhere. It gets changed, goes into the in-stream. And when it comes out of this box, it's the outstream. So it's the outstream that really relates directly to the reference state. Because it's the in-stream, once it comes out of this box, goes into the outstream. So the outstream is just VF 1 plus epsilon A XF. FA V0, 0, 1 minus XF. And CA0, 1 minus XA XAF over 1 plus epsilon A XF. Now, if the x's in these three are the same, what does that tell me about the concentrations in these 3 boxes? They're the same. So I can write the same thing, 1 minus xf, 1 plus epsilon xf, CA0, 1 minus xf, 1 plus epsilon xf. That was easy. But again, remember, the box I want is this box. And this, I'm sorry, these 2 boxes. These are the important ones. These are the important boxes, because they're the ones that go in there. Yes?
Why doesn't the fluoride of the F stream get affected by the R? Would it be some kind of ratio?
Because it's the F stream that comes out of this dash box and the in stream that goes into the dash box. This is a black box. If you don't see what's in here, if you don't know what's in here, something's going in, something's coming out. The recycle ratio is inside the box. It's not outside the box. Okay, so remember, you're thinking what the recycle ratio is affecting is how big stream 2 is. It's not affecting what's coming out, because at steady state, what's coming in is what's going out, modulo the chemical reaction. But by changing R, I'm changing X2. I'm sorry, I'm changing the flow rate of stream 2. Okay, so now let's go ahead and calculate these V's and F's. How do I relate V3 to VF? Who's that? It's on the blackboard. I'm pointing to you.
Right.
Just ignoring me isn't the way to get, it's just going to make me ask you more questions. It's on the blackboard.
VF is, it's minus V3.
Right? Formula's on the blackboard. This is reading. Let's go back to first grade. Reading. How does V3 relate to VF?
It's RV. V3 equals RV.
V3 is RVF. So V3 is R times VF. So this is just R V0, 1 plus epsilon XF. How about V2 while we're at it? What's V2? I'm sorry? No. Stream 2 is not just derived from stream 0, it's also derived from the recycle ratio.
Since V3 is equal to R times VF, then V2 would just be twice as that.
Twice? Why twice? How do you relate V2, V3, and VF? They're all the same. They're all the same. So if I have 100 liters per hour coming out of here, there's 100 liters per hour coming out of here, and another 100 liters per hour coming out of here.
It's just half.
Half. It's exactly half. So if I make the recycle ratio 0, I still have half of it going into the recycle. How about instead of giving me a formula, telling me something that's obvious in English, not a formula? What relationship do we know between V3, VF, and V2? If I asked a third grader, how does V2 relate to V3 and VF? What would the third grader tell me? Yes. Always start with the simplest answer. V2 is equal to V3 plus VF. But and we know VF, so let's get everything in terms of VF. But V3 is RVF. So it's R plus 1 VF. So V3, where are we? We're looking at V2. V2 is R plus 1, V0, 1 plus epsilon XF. Right from that way. Okay, how about F? Let's look at F for a second. Okay, the same relationships between the V's are also the relationship between the F's for 2 F, and 3. Why is that? I've got a stream with a volumetric flow rate that I split up, and I've got a stream with a molar flow rate that I split up. There's no reaction here. So splitting up the molar flow rate and splitting up the volumetric flow rate, they split the same way. So if this was our VF, then this is our FF. If this was R plus 1 VF, this is R plus 1 VF. Okay, that still doesn't give me the boxes I need. I need these 3 boxes to get this one. So now comes the part where we have to come up with stream 1, which is the most complicated stream here. Stream 1 is the inlet plus this. So what can I add simply? Am I allowed to add x's? Am I allowed to add x's? Am I allowed to add c's? No. But am I allowed to add v's? Volumetric flow rates, I can add them. Molar flow rates, can I add them? Yes. So let's add. Stream 1 is in plus 3. So I just add this box and this box. So I have V0, 1 plus epsilon x in, plus RV0, 1 plus epsilon xf. I just add these two now. FA0, 1 minus x in, plus RFA0, 1 minus xf. And now I'm ready to get CA. How do I get CA? Well, CA is FA over V. So CA1 is FA1. FA0, 1 minus, and I can factor out an FA0. This is in both of these terms. So I've got an FA0 times 1 minus x in, plus R, 1 minus xf, divided by V0, so I factor out both of these terms, 1 plus epsilon x in, plus R times 1 plus epsilon xf. And this is CA0. So this now is CA0 times 1 minus x in plus R 1 minus xf divided by 1 plus epsilon x in plus R times 1 plus epsilon xf. So now I'm ready. I'm ready to get the one thing I needed, which was I needed to fill in the whole chart to get. Well, in order to do that, let me invert this equation before I do it this way. So if I know, here I have a formula, if I know x, how to get c. But I know c and I want to get x. So let's invert this. If I invert this, this equation is going to give me CA over CA0 is 1 minus x over 1 plus epsilon x. Let's multiply out. I get CA over CA0 plus CA over CA0 epsilon x. Multiply out the denominator. Is equal to 1 minus x. So let's bring the x's to one side of the equation and the other things to the other side of the equation. So I have 1 minus CA over CA0. Bring this to that side. And bring the x to this side. So I have XA 1 plus epsilon A CA over CA0. So I've just inverted this. Now if I know C, I can get x. So now if this is my C, I'm going to plug into this expression. So I have XA1 is equal to, well, it's equal to